Hello, today I'm going to be discussing topic 2, specifically option 1 of the questions. To start, the first question focuses on outlining the architecture of the CPU and the functions of the ALU, CU, and registers within said CPU. Now, to start, in order to answer this question, we first must understand what the CPU is. It's a key component of the system which focuses on and is responsible for the execution of instructions, so the fetch, decode, execute cycle. And we see this fetch, decode, execute cycle within the CU as the control unit specifically focuses on said cycle. It manages to gather the data from the cache and RAM, stores them within the registers, and in turn decodes them, allowing the CPU to execute them. The ALU then focuses on the logic and arithmetic operations that are required for data. So it takes input from the registers and produces an output which is stored within the accumulator. From here, final thing is registers, which store or temporarily store the data that the CPU require. There's two types of registers, the memory address register and the memory data register. So the first, or the MAR, stores the address of the information and instruction, while the MDR stores the data that is currently being used. Um, Next question is to describe primary memory. So primary memory is volatile memory that is embedded in the system, and as a result, that means that once the device is turned off, the memory is lost, it's gone, and any data information there that was stored there is lost. Now, it is used to store actively running programs and data, and examples include the RAM, cache, and registers. Cache memory increases the speed of the system and achieves this through being closer to the CPU than RAM is. And as a result, when the CPU fetches the data, the bus has to travel less, and as a result, increases the speed. Yet, as a consequence, in order to help with the speed, the cache memory has to be limited. It can't store significant amounts of data, and thus typically only stores the data that will next be asked for the CPU. And in turn, this causes it to be fast, yet it decreases the size of the data that's stored. From here, they want to ask us to explain the machine instruction cycle. Now, there are three key stages for the machine instruction cycle: fetch, decode, execute. First of all, the CU or the buses, they fetch the data from either the cache or RAM, and then they store them within the registers. From here, the CU decodes that data, and in turn, it decodes the instruction and allows the CPU to do the final step, which is execute the instructions. Then they asked us to identify the need for persistent storage. Now, persistent storage is almost a second kind of term for secondary storage. And the fact is, this persistent storage is non-volatile. And as a result, when a device is turned off, the storage or all the files, application software that's stored on there are maintained. This in turn indicates that we need a secondary storage, as there are certain information or instructions that we always need to be stored, such as the BIOS that boots up the operating system, or many essential files and applications. And as a result, we need a way to store them without them being lost. Once the device is lost, loses power, and this is where persistent storage comes into play. Describe the main functions of an operating system. I chose three to discuss: memory management, file management, user interface. The first of which, memory management, manages the primary memory. It manages virtualization and manages scheduling, and as a result, allocates the necessary memory to different programs and applications that are currently running. And here paging also comes into play. And as a result, it has a key part and a key integral part of the operating system. File management, the operating system organizes files and defragments them. And this increases speed and activity in accessing the files, while also leading to an organized user interface when accessing them as well. And finally, the user interface means the operating system provides a GUI for the user that allows easy of use, and in turn increases efficiency. The next question is to outline the use of a range of application software. The fact is, we need application software as the wide variety of said software allows us to create or to commit with many actions within the computer, and thus increases its efficiency and usability. Now, they include, but not limited to, word processing, spreadsheet, databases, email clients, and various other programs. Um, the next question is to identify common features of applications. Typically, applications follow the WIM structure: windows, icons, menus, and pointers. Windows allow for multiple tabs to be open at once, and this increases usability and efficiency, while icons act as almost an identifier to the to different functions and sections of the software. Menus simply improve navigation and the structure and layout of the application, and in turn the usability, while a pointer allows the user to navigate throughout the interface of the application. From here, they asked us to define the terms bit, byte, binary, denary, and hexadecimal. Bit, byte, and binary can all be grouped together. This is since a bit is simply a 0 or 1. It represents either true or false. And as a result, this extends into a byte, which is simply 8 bits, or 2 to the power of 8, sorry, by accident. Alternatively, binary is the base 2 numerical system, so it is the base system for bits and bytes. While denary and hexadecimal differ, denary is a base 10 and hexadecimal is a base 16. Outline the way in which data is represented in the computer. Now, data is represented in bits typically, and the reason behind this is the machine can only understand bits or can understand zeros and ones. But we also use bytes, and we see this when we're talking about memory, or sizes in general. So we say that megabytes, gigabytes, terabytes, these are all bytes times 10 to the power of either 3, 6, 9, 12, etc. And finally, we have also that is represented in hexadecimal for colors, and we see that colors maybe are hashtag FFFFF. So there's 6 digits of hexadecimals, and in turn allows various colors to be represented. We also discuss Boolean operations. Now I group these together since I do believe that the 3 questions can be answered simultaneously, and I'll answer them for each of the operations. To start, we have the AND operation, which outputs 1 if the first and second input is 1. This in turn means, or we can see it in the truth table, where the only time that Q is 1 is if both A and B are 1. Alternatively, OR gates outputs a 1 if the first or second input is 1. So either either A or B can be true for Q to be true. And we see this in the fact that at 0, 1, Q is 1, or at 1, 1, Q is 1. Yet when both A and B are 0, Q is 0. Finally, not finally, but continuing on, not is always the opposite of the input signal. So if A is 0, Y is 1. If A is 1, Y is 0. And that's pretty straightforward. Then we have NAND, which is simply an AND gate followed by a NOT gate. And this in turn means it's the opposite of AND. So in AND previously we said that both A and B had to be 1 for the output to be 1. But in this case, A and B just don't have to be 1, 1 for the output to be 1. And we see it in the fact that 0, 0 leads Z to be 1, or 0, 1 also leads Z to be 1. Then we have the NOR gate, which outputs the opposite of an OR gate, and it's similar to the idea of a NAND, except this time applied for OR. And as a result, only 0 and 0 inputs allow Q to be 1, or in other cases, false and false that leads true to be Q, leads Q to be true. Finally, we have the XOR gate, and now this is just an exclusive gate, and in turn it means that either A or B can be 1 in order for the output to be 1, yet not both can be 1. And we see this within the truth table, and with the fact that 0, 0 leads an output to be 0, and 1, 1 leads the output to be 0, yet 0, 1 for either A or B causes Z to be 1. Thank you.